Hello, this is Monique Morton, Mathematics and Computer Science Director for Advanced Kentucky, and this is the first of several mixed optimization problems to review for AP Calculus. Let's start with the first one. A rectangle is formed with width x and height y such that the point xy is on the graph of y equals 4 minus x squared. What is the maximum area of such a rectangle? So I already presented you with a picture. Sometimes you would have to draw one in these cases, but I've given it to you. Here's my point xy. And notice that since this is the point xy, the width of the rectangle would be x, and the height of the rectangle would be y. So, since we want to maximize the area, we'll need to write a function for area, which is our optimization function. So far we know that a is equal to x times y. But we also want to write our area as a function of one variable. Luckily, we know that this red curve is y equals 4 minus x squared. Therefore, we can rewrite the area function as a of x equals x times 4 minus x squared. And going ahead and distributing the x, 4x minus x cubed is our area function. Now this is a good point to talk about domain. X cannot be any real number. Since we're pretty much limited to this area right here, x can be at the top here, but then I wouldn't have a rectangle at all. So x has to be greater than 0. And x can come down here to the x-axis where it would be equal to 2, but again we wouldn't have a rectangle again. And then if it passed down beneath it, we're going to end up with two triangles instead of a rectangle. So our x value has to be between 0 and 2. Since we want to maximize the area, we need to find the derivative of the area function. A prime of x is equal to 4 minus 3x squared. I'm going to set this derivative equal to 0. 4 minus 3x squared is equal to 0 to find the critical points. X squared is equal to 4/3. So, and that means the absolute value of x is equal to 2 over the square root of 3, which means that x is either negative 2 over the square root of 3 or positive 2 over the square root of 3. But remember that statement about domain, that x is limited to be between 0 and 2. So I can ignore this negative solution since it's not in the realistic domain for my problem. So I have one critical point. It's 2 divided by the square root of 3. Note, this polynomial is never undefined, so I never have to check for that type of critical point when I'm checking for my max or my min. So I'm going to look at the sign of the first derivative between 0 and 2. Now 2 divided by the square root of 3 is somewhere between 0 and 2. It's a positive number and it's clearly smaller than 2. Let's see. I'm going to think of this as a parabola that opens downward, this being the first derivative. And therefore between 0 and 2 square root of 3, I'm going to end up with positive values. And between 2 divided by the square root of 3, I should say, and 2, I'm going to end up with negative values. So there is a relative minimum at, maximum at x equals 2 divided by the square root of 3. However, since this is the only critical point on the interval, I can go a step further in saying it is the place where the absolute maximum area is going to occur. So I'm going to basically translate my sign chart into words as a way of using the first derivative test to justify my max. Okay. So a prime of x is positive for x between 0 and 2 divided by the square root of 3. A prime of x is negative for x between 2 square root of 3 and 2. Therefore, a of x has a maximum at x equals 2 divided by the square root of 3. Now, note that this justification right here considers my entire domain, so I've actually justified an absolute max and not simply a relative max. If I just say changes sign without considering the entire domain, I'm justifying a relative extrema and not an absolute extrema. Now, I feel like I'm finished, but when I go back up here, the question is what is the maximum area, not what value of x gives it to me. So I need to find the maximum area. The maximum area is a of 2 divided by the square root of 3, which is equal to 4 times 2 divided by the square root of 3 minus 2 divided by the square root of 3 cubed. I'm not going to simplify a whole lot, but I'm going to do a little. 8 divided by the square root of 3 minus 8 divided by 3 square root of 3. And let's multiply this by 3. 24 minus 8. I think you can see where I'm writing down here at the bottom. This is 16 over 3 square roots of 3. That's my maximum area. So my steps in solving a problem like this and the steps in solving most optimization problems are pretty much the same. First, back here, we read the question. Make sure we read it and understand what's going on. Sometimes it might be helpful to draw a diagram if one's not given it to you. And if you do draw a diagram, make sure you label it with the given information. Area is what we're trying to maximize. So we need to write an equation for our what we're trying to optimize, in this case the area. And then use whatever constraints we have. Our constraint in this case was that 4 is equal to 4 minus x squared to help us rewrite the area function as a function of a single variable. Now the process of finding the max and the min. We find the derivative. We find the critical points. This time we set it equal to 0. It's never undefined, so I didn't bother to do that part. I checked the sign change for the first derivative to determine the relative maximum. Wrote my justification, and then down here at the bottom found my answer. I hope you find this problem helpful as you review. If you need to look at other problems, you can check out other mixed optimization problems on this site.